This is part 3 of a 4-part series called Introducing Gait Fragility. In this video, we will present an existing simple biped walker model and a controller that we will use to test the gait fragility metric introduced in the previous video. If you haven't seen parts 1 or 2 yet, links to them are in the description below. Also, I will mention a couple of textbooks and a paper later in this video. All of those resources are listed in the description below, so take a look. Introduction. We are using the 3-link planar bipedal walker model provided in section 3.4.6.2 of the textbook entitled Feedback Control of Dynamic Bipedal Robot Locomotion by Westervelt, Grizzle, Chevalereau, Choi, and Morris. You will find a detailed derivation of the dynamics there, and the book is a great resource. A PDF version of this textbook is available online, and I've linked it in the description of this video. The authors of the textbook are careful to point out the importance of considering impact dynamics when working on bipedal locomotion problems. They do not just do this in the textbook, but you regularly find this in papers written by these authors, like Asymptotically Stable Walking for Biped Robots, Analysis via Systems with Impulse Effects. I made the mistake of ignoring foot floor contact and the effects of impacts for far too long in my research, and the work of these authors was helpful for me. Often, only the continuous time part of the robot dynamics are presented or focused upon because it can be difficult to deal with impacts mathematically. It's easier to make assumptions that simplify the math, like let's assume that impact effects can be ignored and that the foot is flat on the floor and doesn't slip. Those things rarely happen and certainly can't be assumed to happen regularly. Here, instead of only showing the continuous time dynamics, a hybrid dynamic model will be presented in 2 parts. In the first, we'll show the swing phase dynamics. This is familiar to anyone who has ever derived the dynamics of a 2-link robotic manipulator, for instance. The second part is a description of the impact model. Here we assume an instantaneous double support phase and a discontinuous transition from pre-impact state to post-impact state. Why? Well, in short, because math gets really hard if we don't. Finally, we will present the complete hybrid model composed of swing phase dynamics and the impact model. If you're interested in the model or controller I'm about to describe, and don't feel like repeatedly pausing the video and writing all of it down, email me and I can send you the section of my PhD thesis with all of these equations. 3-link planar walker. The robot has 2 straight legs, each of length R and mass M, and a torso link of length L and mass MT that hinge at the hip of mass MH, as shown in the figure. The robot angular position vector Q is composed of stance leg angle, swing leg angle, and torso angle, and these are all absolute, measured clockwise from the vertical. These 3 degrees of freedom are controlled by 2 leg torques, each exerted at the hip. We can write the robot's dynamics during the swing phase in a familiar form, shown here, where Q, Q dot, and Q double dot denote robot angular position, velocity, and acceleration vectors, respectively. M is the inertia matrix, C of Q and Q dot is the centrifugal Coriolis matrix, G of Q is the gravitational vector, B is the torque distribution matrix, and U is the input torque vector. Here are matrices M and C, vector G, and matrix B. In M, C, and G, we use the substitutions of C of ij equal to cosine of Qi minus Qj, and S of ij equal to sine Qi minus Qj. As stated earlier, for this robot with point feet, we model each impact as an instantaneous double support phase with a discontinuous state transition. When an impact is detected, a post-impact state is computed from the pre-impact state and supplied as the initial conditions to the swing phase dynamics as a new swing phase commences. We use the following impact model. The plus superscript denotes post-impact and minus denotes pre-impact. We complete the impact model here by describing when impacts occur. Since this robot has straight legs with no knees, a swing foot would drag on the walking surface. There are a couple of ways to deal with this. First, we could assume that the legs have the ability to lengthen and shorten when needed. Second, Tad McGeer, who did a lot of work in the 1990s with passive dynamic walkers, demonstrated that small leg motors could push the swing leg out of the sagittal plane during the swing phase and pull it back when contact is desired. If you're interested, he wrote a paper called Passive Dynamic Walking and another called Dynamics and Control of Bipedal Locomotion. In this case, we will assume that a step or impact occurs when the stance leg reaches a pre-specified angle magnitude. Therefore, the switching behavior described above for impacts will be dependent upon robot state instead of time. The complete hybrid dynamic model for the 3-link planar walker is as follows. The first line describes the continuous time dynamics when the robot is in single support, and the second line shows the discontinuous state transition at impact. Here, state X includes joint positions and velocities, and X minus and X plus denote pre and post-impact states respectively. F of X and G of X are defined here. The impact surface S is defined as a pre-impact state at which the stance leg angle is equal to the pre-specified maximum stance leg angle. Controller design. The design of the controller outlined in this section consists of determining appropriate outputs, designing a feedback linearization controller, and searching for a stable periodic orbit so that stepping can repeat indefinitely. Since there are 2 inputs, leg torque for each of the 2 legs, we define 2 outputs such that walking occurs when they are achieved. The first output is torso regulation. We set the desired torso angle at 30 degrees. The second output is to move the swing leg such that it mirrors the motion of the stance leg. These outputs are expressed below as vector y, which we define as a function h of robot angular position q. Feedback linearization is a simple way to derive a controller that can drive outputs to 0. If we have defined our outputs properly, then driving the output vector y to 0 will result in desired walking behavior for the robot. Let v be a secondary control that is equal to the second time derivative of y. That is, y double dot equals v. We can also define v in terms of Lie derivatives and our primary control u. Here are the substitutions used in this definition of v. We will now design an optimal linear feedback controller v that will drive y to 0 in finite time. After introducing the state variables z equal to y and y dot, the double integrator becomes z dot equal az plus bv, where a and b are as follows. Assuming our control takes a linear form with respect to y and y dot, then the double integrator can be rewritten as follows. We now introduce a performance index, as in the modern control systems textbook by Bishop and Dorf. The optimal control gains that will minimize this performance index are found with the following equation: K equal to R inverse times B transpose times P, where P is the solution of the Riccati equation. If we use R equal to 1 and set Q as the identity matrix, the optimal gains become Kp equal 1 and Kd equal 1.7321. For homogeneity, we apply parameter epsilon to the controller as follows. We set epsilon equal to 0.1 for this controller. With this linear optimal feedback control V fully defined, we can now compute our primary control U. Finally, to ensure that the controller will produce periodic behavior, that is, a consistent walking pattern for the robot, initial conditions for limit cycles must be tested. We found a stable limit cycle for the following set of initial conditions. With a stable limit cycle found, we expect to apply the designed controller to the hybrid model and achieve periodic stable walking behavior. Hope you enjoyed the video. So, we are almost ready to see how my fragility metric stacks up against the balance metrics introduced in the previous video. In the next and final video of this series, we'll show how to compute the center of mass Jacobian for the three-link model we described today, and how to then compute my fragility metric, as well as the other Gait metrics we'll be comparing it to. Finally, we'll actually compute all three metrics and compare them in animations of the three-link walker. Hopefully then, all of this will make a little more sense. Thanks for watching.